So the message is clear. Don't take us for granted. Don't take your teachers for granted. Be sincere in your approach. इस तरह से मत कीजिए. This is almost क्या बोलें, disrespect of worst kind. It basically, even you demotivate a teacher to take class. So why should you take class? तब तो अच्छा है, मगध यूनिवर्सिटी जैसा बन जाते हैं हम लोग, क्यों पढ़ाएंगे? Why should I take so much effort if you are not? Okay. So basic thing जो मैग्नेटिक रेजोनेंस का है वो आपको बताया था हमने. What is the how it happens? You put it nucleus, if put in a magnetic field, nucleus has protons, neutrons, and both of them are magnetic. ये आप जानते हैं. You know now, proton have magnetic moment, neutron also has a magnetic moment. So depending on whether they are present in even or odd numbers, you have a net magnetic moment of the nucleus. They may not have if they both are even, so that also you know. So certain nuclei are said to be magnetically active, the others are not. So those things we have discussed already, we know it. So based on that, we have a technique which is called nuclear magnetic resonance spectroscopy. And it is in the first part we started we are making efforts to understand the nucleus part first. The similar thing resonance can also be achieved with electrons when they are put in subjected to magnetic field, but that will so after a brief introduction of both, because there was similarity of what happens in a magnetic field, how does the magnetic resonance occur, so that was discussed in parallel. And now we are delving deeper, more in depth into the NMR. So first we will be discussing this nucleus magnetic resonance, and once we are done with that, we can go to the other part, that was electron spin resonance, or EPR, paramagnetic resonance. So that will be a later part, but yeah, NMR, we will try to understand all aspects of NMR in detail. It helps when you have a thorough grounding in a particular thing. In the जैसा कि मैं कहता हूँ, if you are operating an instrument, you try to understand each and every bit of it. Don't say that you are a chemist, you don't need to understand this. This is physics. No, this is biology. No. If you are working on something, you have to understand everything. It's science. That's scientific approach. You have to be scientific, not ignore anything. Okay, so that is becomes, so these are instrumental things, and I told you, although I am not going into the instrumental part at this point, we are only related to concept, but basic idea should be there, what and how it is done. So that was a schema. I also showed you a schematic diagram what happens for that. So this was the conceptual thing. Whenever you have a nucleus that you are visualizing, it is having, this is the a nucleus when there is no magnetic field, both plus half and minus half spins, alpha and beta, both have equal energy. When the magnetic field is turned on, when you switch on the magnet, then you see the one the nucleus, the spin, which has a spin which corresponds to magnetic moment aligned with the field, will be lower in energy. So protons, when the spin is pointing upward, the magnetic moment is also pointing upward. So this is the spin angular momentum, and this is the mu. So this one is the lower energy, plus half. And remember, we had the opposite thing in case of electrons. So this is what you know. Non-zero spin, any nucleus will be active. So basically we will be talking about NMR, proton NMR first, then 13, see some examples of 19F, 31P. So this is this setup. Basically you have a superconducting magnet. This we talked about. Main thing, you need to have something around 10 Tesla, something like this. So put a magnet inside the magnet. Magnet जो होगा वो 4 Kelvin पे operate करेगा, because you need to make it superconducting, you need to go to that temperature. There are no superconductors at room temperature. बहुत हॉट फील्ड था एक ज़माने में सुपरकंडक्टिंग रिसर्च ऑन सुपर कंडक्टिविटी, बट नाउ इट्स या अभी तक वैसा नहीं हो पाया कि रूम टेम्परेचर सुपर कंडक्टर को. सो इसीलिए लिक्विड हीलियम की ज़रूरत पड़ती है. सो लिक्विड हीलियम इसीलिए ज़रूरत पड़ता है, एंड दैट्स वाई इट डिफ़िकल्ट टू रन एन एन एम आर. इट मे बी ईजियर टू परचेज अगर पैसा हो तो, लेकिन रन करना हीलियम, लिक्विड हीलियम की अवेलेबिलिटी. Okay, that's something, another aspect that uh, so usually we have so it is we expect the magnetic field to be homogeneous, but it's not always like that. Sometimes you have to rotate it, but that is to be avoided. So these are the things I told you also in the last class, that we have intensity of a NMR signal will depend on two factors: the population difference between alpha and beta states, and so of course you will if you have large in the lower energy state, that is for if you are assuming a proton nucleus, seeing nucleus as a proton. For example, if you have hydrogen atom, there is only one proton. So imagine from that point of view. So if you have 1 mole of them in a container, some of them will be in alpha state, some of them will be in beta state initially, because both the energies was without the field, both are having same energy. So you can expect them to be equally, probability of finding alpha and beta would be same, because in absence of any magnetic field. Okay, but as soon as you apply a magnetic field, there will be a greater proportion in alpha state than the beta, and that's why when you give energy, then alpha to beta transition can happen, right? So if you further probe into what this alpha and beta population difference, n alpha and minus n beta, depends on, you get to know that this is depends on gyromagnetic ratio. It also depends on the field, and obviously the temperature. As the temperature is increased, you can have more and more, you are anyway providing thermal energy which can promote them to the next level. So so what it means, that intensity has finally, if you look at it, intensity has b naught square. So square of the magnetic field dependence, it depends. So magnetic field becomes very important. You are not so intensity is directly proportional to, in fact, turning out to be square of the applied magnetic field. So it is higher the magnetic field, you will get good signal, your analysis will be good, you easier, but much easier, because of course whenever we do something, we would like to see the signal very clearly, as clear, not to be confused with the noise. नॉइज जो अनवांटेड सिग्नल आते हैं ना कुछ, उसको हम नॉइज कहते हैं, हर एक इंस्ट्रूमेंट में होता है. तो नॉइज को we an instrument is said to be good if you have very very small signal insignificant, and the actual sample has gets generates more signal. So something like that, if it happens, we say that it has good signal to noise ratio. Any instrument we will like to have that good signal to noise ratio, and that will be good, expected to be good if we have good high magnetic field. Intensity goes up, population difference. Okay, so overall you have proportionality going to this. So so high magnetic field simplifies your thing. This is the main thing. One, So even producing that 10 Tesla field is a very troublesome. It is a challenging task because the 10 Tesla is a huge field. I was in US. There was a national high. I went to the National High Magnetic Field Lab, and they were having the max strongest magnet in the world. What was the strength? 45 Tesla. So मतलब सोचिए कि that is the 45 Tesla is in the whole world. there is one magnet which is, so ये जो 10 Tesla यहाँ पे हम कह रहे हैं ना, 10 Tesla भी उस लेवल से आप सोचिए कि 10 Tesla is also a very big thing to achieve in normal labs that we if we try to do that. So that's why you see that NMR things are so expensive because of the uh, you know this superconducting thing and the need to keep that maintain it at very low temperature. ये कट क्यों रहा है फिर नीचे? ये हमारा it spoils my rhythm. ये एक peculiar problem हो जाती है. I don't know why. So okay, so 13C and so 2 points regarding this population, and the third point I told you that it is also dependent on magnetogyric ratio. And in this context, I told you that there are mm, uh, so a proton, the hydrogen nucleus has higher magnetogyric ratio as compared to 13C. So 13C. So remember magnetogyric ratio we introduced as a constant of proportionality. Okay, so that so I told you that magnetic moment is directly proportional to the angular momentum in a when a magnetic field is applied. Okay, angular momentum. So that gives you uh, so and that proportionality constant is the magnetic gyric ratio when you do this, and that has been found to be much more for proton as compared to 13C. So you can also expect the nucleus having a greater higher large value of magnetogyric ratio to have an intense signal, a high signal intensity. Okay, so that's I think something that you will observe. You can also uh, local field so if you are looking at the nucleus, you are applying certain field, but there are also electrons around the nucleus. They will generate their own magnetic field. So you can think of, because of this kind of orbital angular momentum, there will be another set of so you can expect like when you apply magnetic field, the electrons will circulate in a particular fashion like a ring around a central point, the nucleus, something like this. So that additional field will be created, del B, denoted by this del B, and this del B has to be accounted for. So when we are talking about the actual field that acts upon a nucleus, uh, that will be something that original strength and plus minus of something, this field that we can have. So plus minus this local thing that is being generated. So so what we are talking about is this electrons which are around the nucleus. So they can have a shielding effect. uh, they shield the nucleus to experience the full magnetic field. They act as a shield in coming in between the magnetic field from the outside, which is trying to come in, approach the nucleus. So something that will be a obstruction, putting something like that. So because they are negatively charged, they can also generate their field, which will maybe countering that field. So usually this sign of usually is positive, and we will see in certain cases where it turns into, that will come later. uh, hmm. So it depends on, so a lot of things that happen. So there is a electronic structure around the nucleus becomes important. And so what happens, the same atom, the hydrogen atom, can come into the nucleus of hydrogen atom will come into resonance, will have different Larmor precessional frequency if it is bonded to different atoms, or mm, same atom but different, like sp2 carbon, or like that sp3, they will also have different. So because the nature of orbitals changes, the electrons circulation will have a different pattern, and so you can have expect the local magnetic field to be different. So their Larmor precessional frequency will be different, and they will resonate, they will come into resonance at different frequencies. So that is something that happens. And so we try to understand this overall local thing. So B naught, the applied field, plus this del B. So sigma, I told you that it is minus sigma B naught, the local field. So you can expect it to be like this, and the Larmor frequency becomes this gamma into, so this is the gyromagnetic ratio into this local magnetic field by 2 pi. So one complete oscillation is 2 pi. So time, so this becomes your frequency, and this is the expression that you can have. So taking original magnetic field, applied field, the external field, so 1 minus sigma, that is the shielding constant, by 2 pi. So this is the important point. For the same element, different frequencies will be obtained because the local environment is different. And usually we do it by express this thing, the change in frequencies, with del sign. This is the, what is this? This is called chemical shift. Chemical shift. So what is the shift in the frequencies as compared to a standard reference? And the reference is TMS, tetramethyl silane. In short, we call it TMS. So when this is there, so 13C. So the references that I told you, TMS is also a reference for 13C, because you have to take care that all the methyl protons, methyl groups that you are talking about in a molecule, they are all 13C. And then the resonance that you see, that will be the standard frequency. From that you start comparing the others. So similarly, H3PO4 is used for 31P, and so you can have a list of that depending on what kind of nucleus we have. The advantage, what is the advantage? If you express your result in terms of del, then it is independent of magnetic field, and that makes sense. It becomes easier to analyze for different, if same sample analyzed with two different instruments, you can still compare them, because because they may have different frequencies, different del scale will still remain same. So you can also, if you know the shift in chemical shift value, you can calculate what is the shift in frequency. Okay, so when we talk about 1 unit of chemical shift, sometimes it is referred to as ppm, but that there has been some yeah, you can also write, many books are writing it, no problem. But there's some, in some quarters there is some reservation about that ppm should not be used, or whether it should be used anyway, uh, because ppm usually we refer to concentration, so sometimes it becomes controversial. Okay, so del is 1 unit chemical shift. As you can see, it is dimensionless over here. So so you can simply calculate it. You put the original value, so del this arrow. So I was so value of chemical shift and value of the operating frequency 500 megahertz. So that's then you substitute it and you got that 500 hertz difference. The same thing if the same nucleus put at at 100 megahertz, if the system is operating at 100 megahertz, then the difference between the two will be 100 hertz only. So it becomes sometimes difficult to analyze, to have. So it is also preferable that radio frequency range is kept high. High magnetic field, high radio frequencies help you having a greater resolution. So usually so this is what we can on substitute. So Larmor frequency expression, this is what we get when we substitute for the local field, the actual field that is experienced by the nucleus, which is usually a diamagnetic field, but not always. Usually not always. So we will see in some cases it is a paramagnetic field that it adds up to the overall field. So that will happen in case to case basis. We will see. So if you substitute this value for all of them for the standard, so this is for the reference reference TMS, and this one is for your sample that you can put it. So in this manner you can define in terms of so there is a, if you look at the tetramethylsilane, you can expect the protons are having some electron density. They are having a bond pairs around them, CH bonds. So the electrons, those electrons will also come into circulation. They will, when the field is applied, and they may produce a shielding for that for the nucleus. So you are comparing. So when we are talking about mu naught minus mu, we are actually comparing the shielding that happens in methyl groups in that TMS and the shielding that happens in your sample for the proton in your sample. So in that sense we can reduce this to an expression. We can formulate or derive an expression that relates the chemical shift with respect to the this, what is this? This is the shielding constant in reference, and this is the shielding constant in sample. So shielding in sample, and this was the shielding in reference. So around the same nucleus, that is proton. So as the shielding, so what this expression tells you, shielding becomes, if the shielding decreases, del will increase. Clearly you can see this. If del becomes smaller, this chemical shift will increase. As the shielding becomes less, so this will increase, because you see it is appearing as a negative sign in the subtraction. So smaller is the value, more the del will increase, the chemical shift will increase if the shielding becomes less, or in other words we can say larger chemical shift will be obtained if the nuclei are strongly deshielded. Okay, if strongly deshielded, that means the sigma is less you are talking about. So strongly deshielded means sigma having a small value, and in this case you will obtain larger value chemical shift. chemical shift value will be large. So this is the first thing that we learned. Now this is what the ranges are. The upper panel, look at, ध्यान दीजिएगा। आप ये चीज दिमाग में बिठा लीजिए, यहाँ पे जो दिया हुआ है, so at least you will have some idea what to expect when you look at NMR spectrum. So you see this, you can also note that in these curves, this I usually, so the upper panel you are having is for yes, this one. You can see the scale is from, it is running 0 on the right hand side and 14 going up to the maximum of 14 on the left hand side, right? So this upper panel is about resonance of protons in the, प्रोटॉन मतलब हाइड्रोजन एटम की बात हम कह रहे हैं, हाइड्रोजन एटम में जो न्यूक्लियस है उसकी बात कर रहे हैं। व्हेन वी से प्रोटॉन हियर, इट मींस द हाइड्रोजन nucleus of hydrogen atom, 1H. Okay, so 1H under bound to different having a different environment. So a proton which is bound to carbon CH2, this is CH. So see, they are appearing very close to the zero line. Then as you move to the left, you see the chemical shift increases, having so having a oxygen here, like in alcohol, single bond oxygen with a single bond with a hydrogen, ROH alcohol. So there also you can see there's it is appearing here, aromatic alcohol, aliphatic aromatic alcohols, then amide you can see, then ester, ketones appearing on this side, you can see. So there's a difference, a lot of difference between, so because of simple change in the bonding situation, the electronic environment changes, and you have each of these protons are coming into resonance at different frequencies, and that's why you are able to identify the looking at the spectrum, you can identify what you have in your sample. ठीक है, what group is present in your sample, that can, and what proportion, किस रेशियो में है, सिग्नल इंटेंसिटी का रेशियो देख सकते हैं, उससे भी आपको बहुत कुछ आइडिया मिलता है. So this is the primary thing that we learn. So the ranges, so max at the other end, on the other extreme, on the extreme left पे क्या है, on the left hand side you see left hand side here you can see the aldehyde group is here. So this double bond C double bond, this proton with a double bond with a carbon which is doubly bonded, you can also have here. This is also a proton which is having a carbon bonded to having a double bond with oxygen. The acid, so the carboxyl acid appears at the extreme of this, that what we are seeing over here. Similar thing you can compare for 13C resonance. Another thing that you can note, so compare the two scales now, carbon 13C resonances. What you see here is that it is what you see in this is about the resonance of 13C nucleus. So first thing that you note is that the scale is it is going up to, the chemical shift values are going to 0 to 300 in the scale. Look at the x-axis. You have starting from 0 to going up to 300, and so you have a larger values of chemical shift for 13C resonances. So the shift in frequency is huge in this case, रिलेटिव. सो जहाँ पे 0 से 10-15 तक खत्म हो रहा था, यहाँ 0 से 300 तक जा रहा है. So that's a big thing. So carbon, so you see here when you compare it with the carbon 13C carbon in TMS, trimethylsilane, you find that so 0 means you are having no difference as compared to the trimethylsilane, tetramethylsilane, right? And when you say you have a chemical shift of this, that means it differs by a. हाँ सर, गुड मॉर्निंग. ना अभी क्लास ले रहे थे. हाँ हाँ, अभी क्लास चल रहा है. थोड़ी देर में हम करते हैं आपको फोन. हाँ, क्या चीज? अच्छा, थोड़ा टाइम लगेगा हमको. 10 बजे तक तो क्लास ही लेंगे. अच्छा ठीक है. हाँ ठीक है, हम आपसे बात करते हैं थोड़ी देर में. हाँ, ओके. ओके. सो क्या कह रहे थे? हाँ हाँ, यही कह रहे थे ना. हाँ. सो यू कैन सी, वी विल ट्राई, ऑफ कोर्स वी विल बी discussing all these kind of things that we are seeing over here later. So one by one we'll try to understand. So it is somehow related to the electron nucleus of 13C, electrons of that particular atom where the nucleus is located, then electrons in the neighboring atom, and all of them create a field. A field. So when we were talking about hydrogen, the proton, we were talking about hydrogen atom, the nucleus of hydrogen atom, the electron. A hydrogen was in one electron, and that is getting shared with carbon. So immediately that came into picture, and then the neighbors. Here the carbon atom, which has a greater number of electrons around it, so definitely they will have a de-shielding effect and all those. So the shift is coming out to be greater. You can see this happening over here. And so shift in frequency is, so first the electrons of the same atom where the nucleus is located, then the neighboring atoms, all of these are contributing to the overall picture, the overall field that the nucleus of your interest actually experiences. So here so in the second panel, the interest is on, our interest was with 13C, and that's why we, so we'll come to the points. But you can see in this case also that double bond O, C double bond O, the aldehyde, the ketones appear to the extreme position in the around 200-300 range. Okay. And other CC appears in this middle. So there is something special about, so in both cases you are seeing there is something special about these double bonds, triple bonds, double bonds, that is there somehow. They are lying towards the one thing common that you are seeing, that aldehydes are lying in the towards the extreme of positions, having a higher chemical shift in both the cases. And so क्यों, क्या, कैसे? So obviously we are talking about two different nuclei in these two cases, and the immediate environment will be affected. So what we have seen in just in this graph, we can correlate few points, we can understand few points over here. So carbon is more massive than hydrogen, so you have greater number of electrons. This is the point I have already told you, that if you have a greater number of electrons, so compare, so more massive, you if you compare 13C is heavier, massive, I mean having heavier नहीं लिखे, more mass, greater mass than 1h. That means we are talking about it has so yes, a large number of large number of electrons around the nucleus. So large number of electrons around the nucleus, right? So around the 13C nucleus you have a large number of electrons, and so there will be a range of shieldings that you will achieve depending on conditions. So slight variation in the bonding situation, you will see a gradual change even in the same family of so that you saw that ये देखिए, look at the value R3C plus, huge, the range is this, so a variation of thing within the same family of compounds. So like this you can see the variations for the same family, huge. So things like this will appear because of this. You can have many shades of variation, like a color का होता है ना, कितने सारे shades आप create कर सकते हो. So shades of variation will be more in those cases. There is one thing that on an average in which range they will come, but there are huge variations that you will see when you have. So so few things that you have learned so far is that the spectra that you have just seen from right to left, look at right to left, Larmor frequency also increases from, so that means when we are talking about shift in the frequency, so the frequency is increasing when we move from right to left. Larmor frequency is different. So the spectrometers that we usually operate, there are different types of, but the simplest one, NMR spectrometer, the simplest NMR spectrometer is something that is called continuous wave spectrometer, which has a radio steady constant radio frequency is emitted, and the magnetic field, so radio frequency is held constant, and magnetic field is varied. So this, so field variation in field, the radio frequency source is kept constant, okay. So but the field was varied. So if you uh, keep the radio frequency constant, so each of the nucleus has to come into resonance, uh, because they have different Larmor frequency. You must change the, because the frequencies, uh, so to bring into the resonance at the same frequency, you will have to apply different magnetic field. So that means you will gradually change the magnetic field until you see a signal, until you see a resonance being achieved. So this was spectrum was displayed with the magnetic field left to right. So small chemical shift means low. So in general, you can correlate few things very easily. Small value of del, that means low magnetic field. Local field is low. Something appearing showing a. So if you are talking about, so when you see if the local field is low, that means you will have to apply a higher external field to bring it into resonance with the radio frequency. So in that case, लो लोकल मैग्नेटिक फील्ड मतलब आपका जो शील्डिंग मैग्नेटिक फील्ड लो क्यों हो गया, क्योंकि किसी ने उसको अपोज किया है. समथिंग इज देयर विच इज अपोजिंग दैट अप्लाइड फील्ड, external field, and that's why the local field, actual field that it experiences is less. So that is, you say that you are having a very highly shielded thing, or what you say is that so what you can say that uh, when we say that small chemical shift, so right hand side was the area in the spectrum. Previous slide we have seen, right hand side you were having 0, then 1, 2, 3, 4, like this, small chemical shifts. So that represent a low value of local magnetic field. Small shift, low value of local magnetic field. Why it is low? Because you apply the same magnetic field to all of them, but some locally they are experiencing low magnetic field because they are having a greater shielding. So something, so you can say, so because they are having greater shielding, you need to apply a shielding. So to bring it to the resonance, you must apply a high amount of magnetic field, external magnetic field, to bring it to resonance. So that's why we say that it is high field end of the spectrum. The one where you are having a lower value, sorry, the left hand side where the chemical shift is high, that is a low field spectrum. So this is the point of view from the early spectrometers, where the magnetic field was varied, radio frequency was held constant. So to bring it into resonance at the same frequency, for all the, when you're trying to bring them into resonance at the same frequency, the magnetic field should be changed. Okay, so with that idea, we call them high end. So right hand side is called high field end of the spectrum, and the other side that you see, okay, and the vice versa. So typically, so we are having, एक minute. So what I was saying, so this is a typical spectrum uh, for ethanol. So simple spectrum. So this is a good example to start with. When we are looking at ethanol, this is the spectrum that we get. So you see that methyl protons, CH3, the protons attached to CH3 group, the appear at around 1.2, the chemical shift. You see the methylene, CH2, appears at 3.6, around this, and 4.0, this is the proton with attached to oxygen. So see, different chemical environment for the same element, same hydrogen atom, brings them into resonance. The hydrogen nucleus comes into resonance at different frequency. You can also see the variation in signal intensity. So when we look at it very carefully, you also see that here you have 1, 2, 3. The At 1.2, the methyl protons show splitting in of 3. However, we will analyze the splitting pattern in detail later on. But still, what you are observing, you can say uh, the reason for splitting, all these things will be discussed in detail at a later stage. First, we are trying to understand the intensity, the shift that we are obtaining. So this is what you see. Uh, you have four closely spaced lines. We call it. So this is a quartet. Four lines. So the spacing between them being same, they are quartet. One thing split into four. One signal which has split into four, and here one signal that has split into three. So this is called a triplet. So this is based on a signal which is which in case of an isolated methyl group, imagine an isolated methyl group, the 3 CH3 should have experiencing the same magnetic field, okay, and all of them should have come at one frequency, but slightly difference you see is coming up and splitting into three because of that. That means amongst them there is some difference, and this is appearing, we are seeing two more frequencies appearing. So this is the splitting of the original signal because of the some influence of neighboring atoms. We will analyze that in detail later. And here you are having a quartet splitting into four, whereas the oxygen, the proton, that is it appears as a singlet. So this is a single peak that you see. There is no further splitting of this is appearing as singlet. So we will see why it's happening. There many more things, but another important thing is that experiences the CSC protons form one first group that we are seeing on the right hand side. Almost del is close to 1. Two CH2 protons in a different part. um, so different environment, different location, so they experience different kind of local field and resonance. They come into resonance at 3.6 value, the value of this what you say, the scale, the del scale. And finally you have OH, which is the hydrogen of the attached to oxygen, which is coming at the at resonance as del 4. So increasing value, what does this mean? Looking at this simple molecule, what does this tell you? It one thing is very clear: oxygen appearing, the hydrogen which is bound to oxygen is appearing at a very extreme end, the far end of the spectrum, so far left side. So this is oxygen is more electronegative, withdraws the electrons, and so you can when the electrons are withdrawn from the vicinity of hydrogen, that means you are removing the electron density around the proton, the nucleus of hydrogen. So there will be a strong, you can expect that the proton is strongly deshielded. This is something that is easier to understand first thing. So electron density around that reduced electron density, reduced deshieldings. So it will experience it will come into resonance at a low field. So the right hand side was the high field thing, and relatively as compared to the reference, that was a TMS, उसके कंपैरिजन में अब वो बहुत, ये वाला जो प्रोटॉन है वो काफी, so and in comparison you can see the methyl protons which are not having away from the oxygen atom, not bound to them, so they are least deshielded. So strong, so usually we refer to the spectrum in these terms: deshielded, highly strongly deshielded, or least deshielded. That becomes slightly easier to say rather than shielded, or you can there's nothing much different, like if you use the word shielded and not shielded, least shielded, but sometimes it goes with the this thing, so it becomes so methyl protons are appearing on the far right side, hydroxyl proton appearing at the far left side. So this is clearly a difference that we can see, the electronegativity thing that you are seeing. You can also note one more point, that the absorption lines for the chemical group CH3 group appearing as a triplet, so overall intensity how will you get the intensity, total intensity of CS due to CS3 groups? That is the green line that you see. It is integration that has been performed. Area under the curve is the integration. So you already know in origin you have performed, when you have a graph, you performed this differentiation. You can also do in such programs, the software programs are there. You can also perform integration, and integration means area under the curve. So if you have three peaks, so you sum up the area under each of these three peaks. So then you are getting a software shows you a line which is, so this is the integration profile. The green one that you are seeing is the, this thing is the step like thing that you are seeing is the integrated intensity. So this one is the integrated intensity obtained by taking area under the curve. Graphically it means you have to take the area under the curve, each curve, and then you can get this. So this is, you can see the high value. The other one, you take this second, come to the 3.6 region, chemical shift of 3.6. Here you integrate, perform the integration. It is less value, the area under the curve, integrated intensity is less. And when you look at the intensity here, this is the lowest. So intensity this is the integrated intensity that I am talking about, area under the curve. When you calculate the, so in other words, if I calculate the area under the curve for all these three regions, we find that area under the curve is maximum. So the integrated intensity is maximum for the CH3 protons, it is least for the OH proton, hydroxyl proton, and it appears in the ratio of, if you look at these three ratio, uh, signal ratio, intensity ratio, it is intensity ratio is turning out to be 1:2:3. So this is for OH, this is for CH2, and this is for CH3. So three protons, the integrated intensity. So integration has a very significant role. जब आपके पास ग्राफ आ गया, आप इंटीग्रेट करेंगे उसको, एरिया अंडर द कर्व निकालें, मैथमेटिकली पॉसिबल है, ओरिजिन पे आप कर सकते हैं, मुश्किल नहीं है। जैसे आपने डिफरेंशिएशन किया था वैसे आप इंटीग्रेशन भी कर सकते हैं once you have. So this, if you do it, you can see that the overall ratio is coming out to be, and this is the ratio of the number of atoms of each type. So hydroxyl, only one atom of this type bonded to oxygen. There are two hydrogen which are bonded to in carbon in the second position. So 2 and 3, CH3, there are three hydrogens. So in the ratio of intensities tells you about the relative population within the molecule. उसी molecular formula में कौन कितना present है, कितना कितना किसका है, वो आपको पता चल जाता है. So any unknown sample if you have and you perform this analysis integrated, you will learn, you can predict in what ratios they are present within the molecule. Okay, so ये आपको पता था कि OH वाला एक है, CH2 वाला दो है, डबल है, और उसका so सिग्नल इंटेंसिटी, so 1 2 3 जो आपको आ रहा है 3 is to, you can clearly see this. So this is the area under the curve, and this data analysis software, you can do this, appears like step like curves. So this is what drawing on the spectrum, and this clearly gives you a ratio of, if you're looking at the other way around, from CH3 CH2 OH, then 3 2 1. Okay, So I was looking at from the left side, then it was 1 2 3, and if you are looking from the other way around, it appears 3 2 1. Nothing wrong with it. So so this you see it happens like this, and so this is important. You have counted the number of magnetic nuclei, and you have also noted the chemical shift values. Now you relative in what ratio they are present. The analysis of the signal intensity tells you that there are two CH2 protons, there is one OH proton, and there is also three methyl protons. So in this way you obtain a very crucial information about the molecules, about a molecule that is you are analyzing. So now we talking about this. So we try to understand more on the shielding, the origin of this term that we are going to talk about. So shielding constant you have due to those electrons that we talked about earlier immediately. Then we also so there is so realize there are three things that we are talking about. uh, you take a sample, it is dissolved in a solvent. Within the molecule you have the atom, so proton and its own electron around it. अपना ही इलेक्ट्रॉन जो है वो कितना है, कैसे है, बॉन्डेड है किसी के साथ, बॉन्ड पेयर का हिस्सा है. So that is one. Then sigma neighbor is the next atom, or the electrons around that atom, around that nucleus. So that will also contribute to create a interact with the applied magnetic field and have some effect. You know the magnetic field is a through space interaction. वो कहीं पे भी एक छोटा magnet होगा वो affect करेगा. So the neighbor is also a magnet. The solvent, maybe if it is magnetic, that will also have something. So overall net total picture will be, so the actual field जो एक न्यूक्लियस पे लगेगा वो इन सब का contribution होगा. There will be a contribution from the its own electrons. There will be a contribution from the neighboring atom, which may be bonded, which may not be bonded to it. Still, the interaction will occur because circulating electrons around this neighboring atom, in a neighbor, you have a nucleus, you have electrons around that. So that will also have some effect. So bonded, non-bonded situation, but it is somehow located nearby that thing, so it can affect it. So neighboring group contribution is the contribution from the group of atoms from the rest of the molecule. Solvent contribution contribution from the solvent molecules if they have this kind of activity. And so so when you look at it overall, you can have diamagnetic contribution as well as paramagnetic contribution. Remember, a magnet, if you look at a bar magnet, I told you to visualize these electrons, protons as a magnet. Just you have a imagination about a bar magnet with having a north pole and south pole. उसी तरह से आप ये सोचिए, एक जो मैग्नेटिक फील्ड होगा जो एक बार मैग्नेट का होगा वो इनहोमोजेनियस होता है, हर तरफ एक जैसा नहीं होगा, ठीक है ना. सो कहीं पे वो अप्लाइड मैग्नेटिक फील्ड को एडअप करेगा, कहीं पे वो different, it will be not aligned to the magnetic field. So that kind of thing can happen. We will see more about this. So you can have both the effects. Yeah, like what I am talking about is that if you have a मेरे कहने का मतलब ये है कि this is your north pole, south pole, this is a bar magnet, and when I draw the lines of forces and I am applying a external field B naught, so what will happen that what can happen is that, this bar magnet has its own field, which you can draw by lines of forces like this. Okay, so you have the direction being, so something, now the important thing to see is this: if something is kept over here, so something, if the some group is located over here, so at this particular point, the direction of B naught and the direction of this field, they are adding up. This is paramagnetic contribution. If you think your point of interest is here around this bar magnet, then this is will be reducing the field. It is opposing the field. So this something that a small nucleus which is kept here will feel a reduced field. So this is what, so test nucleus, this is our nucleus here. It will having, so it will experience a reduction, less field experienced. So overall, so it will have an overall less field experienced by the nucleus if it is kept here. If the same nucleus is kept here, so if the same nucleus is somehow it is here, so here the direction is adding up. So then if this is the nucleus kept over here, it will experience, so direction of B naught is this, the direction here, this small the bar magnet, its own magnetic field is adding up to this. So this is so less field. So this is what we mean by saying that we are having a diamagnetic contribution to the electric field, to the magnetic field. And this one is here, uh, the so the direction is like this, north to south externally. So यहाँ पे वो add करेगा. So here the B naught and the, let me say, indicated by B prime. So here the direction of B prime is, it is B naught plus B prime. Here it was, the total field was B naught minus B prime, something like this. So here there is subtraction, here there is addition of the two fields get reinforce each other. So if I am talking about a nucleus which is positioned like this, it may be bonded, it may be non-bonded state, whatever, but it will experience that kind of effect. So both contribution is likely. When we consider a molecule, we might have this kind of situations arising in different cases, and that's why we are talking about both the contributions sigma d, sigma p. So because we know that, if our, I told you that everything, a magnet is a dipole, it has a magnetic field that you, so any dipole will have its own magnetic field, which is sometimes aligned with the field at some locations. At the same magnet will have in different location, you will, if you analyze, you see that it is opposing the field. It is, in some cases it is aligning with the field. So overall field in some point will be greater, at other points around the bar magnet, when you have, this is when there is external field and the bar magnet, if something, so this is what we are talking about. We are talking about a local effect which arises from these things. A neighboring, how does the neighboring atom electron will contribute? So it is a case to case basis. We will come to these situations where in some cases you might have paramagnetic contribution, that is overall increase in the magnetic field. जितना अप्लाई किया उससे ज़्यादा उस न्यूक्लियस पे फील्ड लग रहा है, ऐसा भी हो सकता है. The same circulation, so this is something that you must understand, that uh, Bar magnet, if you draw its magnetic lines of forces, it is inhomogeneous. It is not as same at every point around the whole. You draw a circle around it, a bar magnet, the magnetic field is at the same distance r. It may have different values of magnetic field. So this is so diamagnetic contribution opposes the applied magnetic field, and you have it shields the nucleus. A paramagnetic contribution mean that it adds up to the overall magnetic field, and they'll increase in the magnetic field, you can say. So it is reinforcement, making it further stronger. Making something stronger is reinforcement. Okay, and we say that it has deshielded diamagnetic. So shielding gives rise to diamagnetic contribution, deshielding gives rise to paramagnetic contribution. So we will be talking about this d. So if it is greater than 0, we say that total local contribution is positive if the diamagnetic contribution dominates, and if the this one dominates, the sigma p. So if paramagnetic contribution dominates, then the overall sign of the sigma local will be negative when you have paramagnetic. So diamagnetic contribution, positive sign of the shielding; paramagnetic contribution, negative sign of the shielding. So this is what we learned. So this is like circulation of charge in the ground state that we are talking about, that gives rise to diamagnetic contribution. So there are electrons, and the electrons start circulating in the ground state around the. So circulation generates a, just like you generate a current around a ring, in the ring, and that gives rise to magnetic. So that kind of thing can happen here. So this circulation opposes the applied magnetic field and shields the nucleus, and usually this is what is given by uh, this sigma d is dependent on E squared mu naught, a constant, the mass of electron, and 1 by r. You are getting a, so all are so 1 by r dependence is there. So this is the magnitude that we can calculate. Sorry, something that can be. So this is called Lamps formula, where we are able to calculate the contribution, diamagnetic contribution. So so this is what the idea that you have. Uh, so imagine this picture tells you something more about it. So you have a nucleus at the center, nucleus, central sphere that you are seeing, and the outer sphere that you are seeing, the big one, that is the electron cloud. You are visualizing the electron which is circulating around the nucleus. Visualize these things, and now you see you have applied magnetic field, the big arrow, this one, and the field that you have due to the circulating electrons. So both will be added up. So electrons start circulating, and the net field is drawn. The picture drawn of the magnetic field that you have is the net resultant magnetic field. So this is how it will look like. Its appearance is like this. So you have lines of this coming out from this. So 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 local shielding for the electron distribution that has spherical or cylindrical symmetry. So we are assuming a spherical one here in the picture as shown. Spherical symmetry of the electron distribution. If we assume that, then this kind of thing comes to our mind. So whenever you have a look at this, inner core, you can have, so there are two things that we need to do: inner core electrons and the valence outer electrons. So inner electrons remain spherical even when it is a part of a molecule. The valence electron distribution may be distorted. So under the influence of when you apply this, so they are circulating electrons. This is the nucleus, and the fields. So this is the applied field in this direction, B naught, sigma B naught. This dotted blue line, dashed blue line that you are seeing is the secondary field, sigma B naught, which is, you can see at the point where the nucleus is, it is opposing the applied field. So applied field is going like this. Sorry, applied field is, so this lines B naught is going like this. This is B naught, and this sigma B naught is appearing like this, sigma B naught, sigma into B naught. So this is the secondary field that is created, and the net will be resultant of these two. Okay, so this is the idea based on these things we are discussing thing. So magnetic field, electrons, so electrons bonding to the proton. So look at the proton, you have, they will start precessing around the nucleus in a plane perpendicular to the magnetic field. So this is the circulating electrons shown over here in the picture. So this is so we have a development of a secondary field which opposes the primary field over here. So this is what we have seen, just discussed that now. So net nucleus experiences a resultant field that is smaller. Obviously it will be, if there is opposition, it will be decreased in the field at the nucleus, at the site where nucleus is present. It is shielded from the full effect of the primary field. So this is the external field, and its effect is less than the expected. So there is so what we have is that external field. So because the field has actual experience, magnetic field has decreased at the site of nucleus, you must increase it sufficiently. Overall field has to be increased somehow, only then it will come into resonance with the radio frequency that is fixed radio frequency. So imagining we are starting from the point of view the radio frequency is fixed, we can only vary the magnetic field. So if initially you have a reference and it was coming to TMS was coming into resonance at certain field B naught, but that B naught, when we are talking about a molecule which is having proton which has showing a reduction in field at the site, to bring that hydrogen nucleus into resonance at the same फ्रीक्वेंसी, वी मस्ट इंक्रीज इट्स एक्सटर्नल फील्ड हमारे कंट्रोल में है, उसको हम चेंज कर सकते हैं, तो वो सफिशिएंटली इंक्रीज करना होगा, देन ओनली इट विल कम. सो दिस इज व्हाट वी मीन बाय you have to apply high magnetic field higher than the reference, as compared to reference, uh, and that is called high frequency region. Okay, so this kind of situations may arise. So diamagnetic contribution is proportional to electron density of the atom that contains the nucleus. So atom that has the nucleus of interest, atom containing the nucleus of interest, so electron density around that उसके proportional होगा. Shielding is decreased if the electron density on atom is reduced. So clearly one thing that you can see, that if there is electron negative atom nearby, which is, and through the bonding it is withdrawing the electrons, then it will lead to, so that will de-shield the nucleus. The de-shielding, increased de-shielding will be there, and there will be increase in the chemical shift. So electronegative atom increase in, so one thing is the correlation. So from this discussion we come to a conclusion that an electronegative atom will increase the de-shielding, and there will be shift to a higher side in the chemical shift. Chemical shift will move to, so this is what the pictures can tell you, what we are trying to. So this same thing is being correlated over here. So you have you apply certain from the external, this is external thing, V नॉट, कैपिटल V नॉट. इंटरनली जहाँ लोकेशन है वहां पे ये ब्लू जो कलर में आप देख रहे हैं, शील्डिंग मैग्नेटिक फ्रॉम, इसका जो इंड्यूस्ड फील्ड है वो उसको अपोज कर रहा है. द इंड्यूस्ड मैग्नेटिक फील्ड बिकॉज ऑफ द करंट, ये सर्कुलेटिंग इलेक्ट्रॉन जनरेट अ सेकेंडरी फील्ड दैट इज बी नॉट, और ये जो है उसको अपोज कर रहा है. सो इफेक्टिव फील्ड जो एक्सपीरियंस कर पा रहा है वो इतना ही है, ग्रीन वाला, experienced by protons. So in order to achieve resonance, you must make it, this must be increased, this additional factor to be at the same level. So resonance condition achieve करने के लिए you must apply a higher field now. Okay, so this is what the origin of the things are, and you can see the effect is clearly there. So see, methane, bromine, chlorine, fluorine. So gradually electronegativity increases for the substituent, increasing. So what we see clearly, electronegativity. So increase in electronegativity clearly makes it, the electron density shifts to the, sorry, electron density is moving away from the protons, and which we are interested in, and because of that the electrons are getting the nucleus is proton is now more de-shielded, and it moves to a higher value of the chemical shift. Increasing de-shielding gives rise to larger value of chemical shift. So bromine, chlorine, fluorine, you can compare it going to the higher side. Fluorine is more electronegative, it pulls the electron towards itself, decreasing the electron density around protons. So less diamagnetic shielding, low electron density around proton, that will bring less diamagnetic shielding, and overall the B effective, stronger B effective, and you have, it comes into so you have it will resonate at a higher frequency. So in another words, you can also say the electrons are pulled away by this from the site of protons, de-shielding, leaving them exposed to B naught. So original जो force लग रहा था B naught का, वो लगभग जितना de-shield होता जाएगा उतना वो strong net force will be more, and so it will come into resonance at a higher chemical shift value. So you have a shift in the chemicals, there's an increase in the chemical shift values that we see in these cases, and similarly we can also find so trends are very clear. Chemical shift, so you have to analyze how much de-shielding is happening near a proton. How much de-shielding near a proton? This, if you are able to analyze, you can easily explain and predict the chemical shift values. So trichloromethane, chloroform is expected to be at higher chemical shift value as compared to chloromethane. So see, the first picture was only substituent, one substituent was changed, and then the substituent was gradually changed with higher electronegativity atom. Now what, this is another question that may arise, that if you substitute 1Cl, 2Cl, 3Cl, what will happen? So again the trend would be similar, you can see here. So replacing one hydrogen with one chlorine shifts 3.05, two chlorines, a huge greater shift to higher side, higher chemical shift is obtained, 7.2. So 3 in a chloroform you can expect uh, because of the gradual withdrawing of electron from the site of carbon which is bonded to hydrogen. So CH, so in relation to that the so in the vicinity of this the electrons are gradually being, electron density is moving away from that site, and so the de-shielding effect is less and you have a higher value of this thing. So within one, so this de-shielding effect can also, you can see within one molecule, if a Cl is present, there's, so this is immediate vicinity, you have two hydrogens that you can see appearing at very high value, 3.42 of chemical shift values, and gradually you see one b type electrons which is slightly away from Cl, थोड़ा सा असर होगा लेकिन shifting, so there is less chemical shift value and less for this and least for this methyl protons. So now what you are seeing that because of a presence of an electronegative atom, the CH2 protons of this is also CH2, this CH2 V type. So within methylene protons we can see this is also CH2 group, but depending on how close they are to the electronegative atom that can withdraw electrons, you can see there is some change compared to a CH2. In ideal case, when there is no electronegative atom, it appears at a lower value due to the presence of Cl. The first, which is directly collected, there is maximum effect 3.42, very good shift, very strong shift in the signal in chemical shift values you can be seen. This is also CH2, this is CH2 which is A type directly bonded, alpha, beta, gamma. So you have alpha position, beta and gamma. So the effect of Cl atom in withdrawing, the withdrawing effect that you can see, that is gradually decreasing, and therefore you can see the effect that is relevant. So in this manner you can analyze for other set of any such atom that is present. You can correlate and explain that. It will also depend on sp2 hybrid or whether it's sp3, so electronic. So maybe we'll continue the discussion next class on Monday. So ठीक है, okay, I'm closing this.